So welcome everyone to the evening session. So we again have Professor June E, who will be giving his second lecture in the school today. And I believe he will be talking about potassium rubidium molecules and degenerate gas of polar molecules. So welcome, Professor E.
So good evening, everyone. Following yesterday's discussion about general theme of cold molecules, today I'm going to tell you about specifically getting molecules into the deeply quantum degenerate regime where molecules are so cold and the density is sufficiently high that the Broglie wavelengths of each molecule now overlaps with their neighbors. And so you start to study a collective behavior of molecules, especially if you turn on the interactions. And that's been difficult in the cold molecule physics, where typically you turn on electrical field and so on. The molecules are just not very stable. And that's been a feature that's being plagued this field for the last, I would say, 2 decades in the existence of the cold molecules. But that issue has finally been resolved. We can now turn on electrical field and find a way to shield from the molecular loss. And you can even see to the bottom right corner, the striking features of resonances. When two molecules come together, you can actually use electrical field to adjust, to control the loss coefficient by 3 orders of magnitude. You notice the vertical scale is actually in log scale. And these are really very new features of where we can use electrical field to help turning on interactions which are elastic, while help you shield away the lossy part of the interaction. So finally, we have achieved the goals of being able to make a degenerate gas of molecules and also making molecules to be confined in different spatial geometries. The one to the left is showing how the molecules are confined in individual pancakes of a 2-dimensional traps formed by a 1D lattice. And in fact, in the middle, it actually shows the real image of these molecules in the optical lattice. So this is a quite exciting time that quantum gas of interacting molecules are finally here. Now let me go on to the next slide. As I promised yesterday, and you may have heard that story from Christoph Neger's talk, Hans Christoph. And the idea is that if cooling the molecules directly from once you already have a molecule and cool them down with laser cooling and or other buffer gas cooling techniques that I mentioned yesterday. And of course, the other way to, as I mentioned yesterday, the other way to start making cold molecules is start with cold atoms and find a way to associate them. So that's what the work we did. Now it's almost 13 years ago when we produced the degenerate gas of fermions. This is also something that Sourav mentioned yesterday during the introduction. And then we make also a Bose-Einstein condensate of rubidium atoms. And you bring them together through a coherent conversion process, first through the so-called Feshbach resonance, to bring them into a loosely bound molecular state. And using a pair of lasers which are coherent with respect to each other to do this so-called stimulated Raman transfer, where the population is transferred from the initial near dissociation Feshbach molecule state into the deeply bound ground state through the intermediate states, but you never actually occupy for the population in the intermediate state. Doing so, you actually can achieve a coherent conversion process without any loss and also without introducing any entropy into the system. So this was a work that has been the workhorse in this field of making the so-called bi-alkali molecules, putting together 2 ultracold atomic species and make a molecule. At the time, back 13 years ago, we achieved a temperature of a few hundred nanokelvin, density of 10 to the 12. And because you are pairing up a fermion with a boson, so the composite molecule, the molecule itself is a fermion. And typically you use a Fermi temperature to describe how deeply the gas of atoms or molecules got into the degeneracy. So the temperature T over TF indicate the degree of degeneracy. The lower the temperature, the better. You want temperature to be, suppose 0.1 times the Fermi temperature, then you're deeply into degeneracy. 0.6 is where you start to see degenerate effects, and so on. And I want to take this opportunity, of course, to also highlight there are a lot of international efforts now going on worldwide using this particular approach to generate ultra-cold molecules. And many exciting results are coming out. Some of them I will cover during this talk. And I also want to remember Debbie Jing, who was a long-time colleague and collaborator. She helped create this field. She and I collaborated on this project for many years, but unfortunately she passed away at a very young age of 2016. Now we have APS DAMOP thesis prize named after her, and so certainly her legacy lives on. So let me just give you a quick introduction about Feshbach molecules. The idea being these molecules, these atoms, potassium and rubidium 87 is a boson, potassium 40 is a fermion. When they come together, of course, we all know the atom has Zeeman energy levels. You can tune the energy levels with magnetic field. And the idea of behind the Feshbach resonance is that you have two atoms coming together in, of course, before they are forming molecules, these two atoms are free. They are in continuum state. But when they form molecules, however, there can be bound states. By tuning with the magnetic field, the relative energies, Zeeman energy of the free atoms versus the bound state of the near the threshold of the Feshbach molecule, there is a possibility that you can tune the energy of the incoming sort of a free atom pair energy to be on resonance with the bound energy behind the potential barrier, where the molecules actually forming, being formed as a Feshbach molecule. So by tuning this magnetic field, you can tune this relative energy scales and eventually hit this particular resonance, during which you can actually convert a pair of free atoms into a loosely bound molecule. And this is what's called Feshbach resonances. And we can make very large floppy molecules because these molecular states are hardly bound. They are just sort of at the highest level of excitation, just below the threshold of a pair of free atoms. You have seen this picture like yesterday, indicating all these vibrational levels. And we're really forming a Feshbach molecule at the basically just below the threshold. So you can argue the highest level of a vibration excitation here. And this is all done by ramping the magnetic field. Sometimes people do with the radio frequency transitions from free to the bound pair of a molecule. And because it's the distance between the two nuclei is still very large. A typical scales is a few hundred Bohr. They do not support yet electrical dipole moment. The two nuclei are fairly largely separated. They are not yet quite at the point where they're influencing each other's electronic potentials. And it's very easy to be lost because it's obviously very unstable. They can decay through many internal states. They can also be broken apart. So the key idea is, how do we transfer the molecule from the Feshbach state near the dissociation limit all the way down to the absolute ground state without going through all these intermediate states, because there will be jungle out there. You will be completely lost if you let it go through by itself to try to come down the ladder to the ground state. Remember, this is just displaying vibrational states. There's also rotational hyperfine structures, as I mentioned yesterday. So instead, we actually use a pair of lasers that's a phase coherent with respect to each other. So in particular case of the KRB, we have a laser at 970 nanometer and another laser at 690 nanometer. They're different color, but now through the ideas of a frequency comb or using very stable optical cavities, we can make these two different colored laser beams to be phase coherent over certain time scales. And that's the time scale we do coherent state transfer adiabatically. So even though I drew some pictures of the excited state has we actually do not excite the population to the excited state at all. We actually do this in an adiabatic transfer fashion, where the population is adiabatically transferred from the Feshbach state all the way to the ground state without putting any population up there. if you're interested in understanding this adiabatic transfer, it's nothing magical really. It's just creating bright and dark state I mentioned yesterday. And in this particular case, yeah, it's the bright state because the molecule is always coupled to the pair of laser light beams. And the idea is making adiabatic transitions of that bright state from mostly heavily populated in the flashbox state to the actual absolute ground state. As long as you make those as your bright states of your coupling to the light, you can actually make the population transfer without ever going to the dark state, which could be considered as loss. So this process, using this process, the difference frequencies of the two photons carries away the binding energy. And yet, because the process is coherent, you do not increase the entropy. So we can do this process in almost beyond 90% efficiency to transfer the population entirely coherently from the flashbox state to the absolute ground state. Once you get to the absolute ground state, we are in the vibrational equals to 0, rotational equals to 0 ground state here. Electronically is also the electronic ground potential, sigma to sigma, where the two electrons are paired up to form a singlet. But we still have nuclear spins, and rubidium has a 3½ nuclear spin, potassium has a 4. That's the reason why potassium 40 is a fermion, while rubidium 87 is a boson, because you have to have an electron to pair up with a nuclear spin to form integer spins, while the potassium you have a nuclear spin and one extra electron to form odd numbers or half integers of a total spin, and that's why they become a fermion. So you have these 36 states because 4 would correspond to 9 states, and 3½ nuclear spin will correspond to 4 states. So 4 times 9, 36 states total, different nuclear spin mixture. When we initially form the molecules, we are actually in this particular rubidium spin is 1/2, rubidium nuclear spin is 1/2, and the potassium nuclear spin is -3. The potassium spin is actually -4. Excuse me, I misspoke. But we can actually, using radio frequencies, we can actually do this transfer of the hyperfine manifold such that we can move the molecules all the way to the absolute nuclear spin ground state. So now you can see the molecule that we created, this KRB molecule we have created so far, through this completely coherent process. We were able to start with 2 individual free atoms, ask them to come together, teach them how to go through all these jungles in a coherent way, such that you reach the absolute ground state for electronic, vibrational, rotational, and the nuclear degrees of freedom. So now you're absolutely in the ground state. And so then you're really happy. You said, well, I got the molecules in the ground state, so it should live there forever. Nothing is forever, but nevertheless, you expect to have a really long lifetime, just like the atoms living in your optical dipole traps, right? It turns out the answer is no. It turns out there's a chemistry going on near absolute 0. And how did we know that? Is you can look at the density of the molecules confining optical trap, and you end up discovering as the so-called two-body loss process, where the density of the molecules, if you take a time derivative, is as a function of a minus, which indicates loss, a rate coefficient beta times the density squared, meaning there's a two-body loss process. As you wait longer, the density decays down, and the form of the decay follows the product of the density times the density itself. So this is the so-called two-body loss rate. And so this is a kind of an unhappy story. We thought, well, back in 13 years ago, we thought, well, we created the molecules in the absolute ground state. We have a fairly cold samples, 200 nanokelvin, and we didn't have a 1 second lifetime. And we thought we could start to do physics with it. But it turns out, well, they are decaying over a few seconds time scale, and the system is not stable. There's this KRB plus KRB equals to K2 plus RB2 loss going on. Even at such a low temperature, near the absolute 0, they are going away. So our task is, well, first let's understand what's going on. And the second is, if we can understand what's going on, we can prevent it. if we can prevent it, then we can go on to do the physics that I talked about yesterday, whether it's a quantum many-body physics or study precision measurements and so on with the cold molecules. So let me just give you a quick teaser about collisions between identical fermions. You have learned about all this in classical quantum mechanics books. The first thing we know, particles are like waves. When the temperature is sufficiently low, you have to use de Broglie waves to describe their motion. Angular momentum, when I say angular momentum here, I'm talking about angular momentum between the two particles. Okay, it's not angular momentum within the molecule. So as you learn traditional chemical physics, chemistry, molecule kind of a textbook, they would describe everything as a quantum within the molecule. You know, electrons, of course, quantum mechanical and so on. But you in the classical textbook about molecules, they will never think of molecule itself as a quantum mechanical. Typically, the molecule is moving with thermal velocity, right? That's what you learned. But here, because these molecules are moving at such a low temperature, how they approach each other, you have to think about this completely quantum mechanically. So if the two molecules are colliding, you probably have heard the name so-called impact factor, which is a linear momentum times the minimum distance between the two molecules, and that's called impact parameter in classical physics, describing the collisional process. In quantum mechanics, of course, you use so-called S wave, P wave, D wave, which you actually use to describe how the two particles approach each other with different symmetries. S wave will be totally symmetrized wave functions. P is odd and D is even again as you go on. Each one of them carry respectively 0, 1 h bar, 2 h bar, and so on angular momentum. The angular momentum describes the relative motion between these two particles. And then we also know quantum statistics matter. The KRB molecule is a fermion, which means that the wave function must be anti-symmetrized. So when you exchange two fermions, you will have a negative sign coming out of the total wave functions. And that's what's called a Fermi statistics, which also gives rise to Pauli exclusion principle and so on. And so in that case, we know that a so-called S-wave collision is not allowed for two identical fermions colliding with each other, because in order to satisfy the anti-symmetrization of the wave functions, the angular momentum should at least have 1 h bar unit of angular momentum, which is corresponding to so-called P-wave collisions. And so because of you have 1 h bar unit of angular momentum, you have the so-called centrifugal barrier. And this is what I'm describing in a cartoonish way in the bottom right corner here. This particular picture indicating the potential barrier created by this 1 h bar unit of angular momentum when the two molecules approach each other. So now you can understand the basic physics. When the molecules are really cold, you have this, if you draw the picture of energy versus the distance between the two molecules, when the distance, of course, is really, really short, what you will have is actually binding energy here. That's the two molecules are forming a potential energy, and you can even form a bound state there. And you see a little barrier. This barrier is actually formed due to the centrifugal potential of 1 h bar unit of angular momentum due to the P wave collisions. And then you have this at large distance, of course, it's flat. Now, if at a very low temperature, these molecules are prepared at 100 to 200 nanokelvin temperature. How high is this barrier? And it's relatively easy to calculate. You already know there's 1 h bar unit of angular momentum, you know the mass and so on. You can actually calculate the centrifugal barrier. It turns out that centrifugal barrier equals to 24 microkelvin. So you can say, well, these molecules the temperature is well below the barrier, therefore they should be bounced back, right? But in quantum mechanics, of course, there's a phenomenon called tunneling. So these molecules can actually tunnel behind the barrier to have a chemical reactions. It turns out this is a set of formalism that Eugene Wigner and Hans Bethe and all these pioneers in early days of nuclear physics had established to describe how neutrons penetrate through the nuclei to have a nuclear reaction. And it's the so-called threshold law, where the energy is actually below the barrier, but the particles penetrate through by the quantum mechanical tunneling effect. and then the formalism to describe the probability of going behind the barrier, have a chemical reaction or nuclear reaction, turns out to be relatively simple. Okay, so you can see the message here at the very low temperatures, the quantum statistics of fermionic molecules actually suppress chemical reaction because of this barrier, even though it's not completely suppressed. That's why we saw there's a reaction. If these molecules were bosons, instead of rubidium is already a boson, if on the other hand, potassium, instead of using potassium 40, I use potassium 39 isotope, that would be a boson. And in that case, KRB would be a bosonic molecule, then you wouldn't have this barrier. And I would describe to you how we can observe these sort of incredible impact by just quantum statistics on chemical reactions. And that's what's so interesting about ultra-cold quantum chemistry. It's really shedding fundamental light onto this very fundamental process of how particles approach each other and so on. Okay, so, and as I already described, giving you the hint, if you don't have Fermi statistics, well, how do I do that? Either I can make potassium to be a boson, or I can just use two molecules with different nuclear spins. If they have a different nuclear, remember there's a 36 nuclear spin state, I can pick one of the molecules to be at a different nuclear spin state. If the molecules at a different nuclear spin state, they're no longer identical fermions. If they're no longer identical, you do not have to symmetrize the wave functions. It's just a classical physics. If the two particles are distinguishable, you know where they are. And so in that case, you no longer have this P wave barrier because they can actually come approach each other with angular momentum equals to 0 because there's no requirement of an anti-symmetrization. In this case, you can see there's no barrier and the molecules will just come through, covered by the Broglie wavelength, they will just come through and they do not enjoy the suppression. And so this is all very interesting physics that I'm describing in a very simple terms. And it is experimentally, that's what we observe. And indeed, that's the case. When the two molecules are identical fermions, what we observe is this decay rate coefficient beta for two-body loss is directly proportional to temperature T, as we in two different symbols indicating two different nuclear spin states. But as long as we prepare them all identical, you always see the loss as a function of the temperature because it's P-wave barrier. And this is something that was worked out by Eugene Wigner, the so-called Eugene Wigner threshold law. And so in some sense, it's a satisfying that such a complicated chemical reaction process, by going to the ultra low temperatures, it turns out to be a simple line that you can fit all the experimental data, explained it, why chemical reaction rate proceed with temperature in this particular manner. If you, on the other hand, so this is what I described earlier, if you know the angular momentum, you will have this so-called centrifugal barrier, and this is described, this 24 microkelvin centrifugal barrier we have. On the other hand, if you say, well, let me flip a nuclear spin on one of the molecules such they are distinguishable, and then the rate coefficient goes up as experimental measurements indicated by those green square points, indicating the so-called S-wave collisions where they don't have the P-wave barrier, and that's being described by the rate is actually increased by almost a factor of 100 just by flip a nuclear spin, which costs very little energy to flip, and yet it has a fairly large impact on the chemical reaction rates. And this is what you expect when the chemical reaction should be proceeding. Once you get into the quantum regime, you'll see things that's totally different from what you not ordinarily see in chemical reaction laboratories, where things are described by thermodynamics, by statistical averaging, by the room temperature driving thermal reaction rates and so on. This is the quantum mechanical. And it turns out molecular loss actually looks universal. And the recent work by Kang-Quinn Ni, Kang-Quinn is actually a graduate student at the time. She's one of the co-authors of these papers. And she now has her own research group at Harvard. And she remembered, the KRB plus KRB produces K2RB2. And her research group had recently done some fantastic work to figure out what are the intermediate states. This is a picture indicating KRB plus KRB coming together, and they actually form a transient K2RB2 intermediate. This is something I talked about yesterday. Remember when I talked about a reaction of OH plus CO? So Conquin's group was able to now directly observe the K2RB2 star, which indicating an intermediate state that do not live long. They live for about 360 nanoseconds, and then dissociate into K2 and RB2. And they can follow the reaction process by looking at both intermediate state and products to kind of understand this chemical reaction process. This falls in line with the spirit I was saying earlier yesterday of being able to really look at, understand the chemical reactions. You can follow all of its intermediate and the products. The other experiment, which was very surprising, and also a former group member, Dajun Wen, who was a postdoc in our initial set of experiments, he is now a professor in Hong Kong. And his group actually studied the sodium rubidium experiment. And the sodium rubidium experiment also produced sodium to rubidium 2, except that in the absolute ground state, this process is a so-called endothermic, which means NARB plus NARB energy, if they are in the absolute ground low vibrational state, is actually lower in energy than Na2 plus rubidium 2. So unlike a KRB, which is exothermic, this endothermic process, meaning if you're in the absolute ground state, this process should not go, right? Because where does the energy come from? That's why it's called endothermic. What's really surprising is that in Dajun's group, when he prepared these molecules in the ground state vibrationally, or the first vibrationally excited state, what they are observing, as you can see on the data, the two-body loss rate follows exactly the same manner, whether you are V equals to 0 or V equals to 1 hardly matter in this particular case, indicating there's some very universal process going on for this ultracold chemical reaction process. There are a lot of postulates and theory work that's going on, because this is actually a feature of loss that seems to be very universal and in some sense troubling, because unless you can solve this problem, all these molecules you created in the quantum regime disappears, decays away after a few seconds. So if you want to use this to do interesting physics, you have to first solve the loss problem before you can proceed. So this is actually an interesting question about to the community a few years ago. This is a paper was published in 2018. Can we solve the loss problem? So maybe one more slide about this loss process. There's also, I haven't even turned on the electrical field yet, or the loss we described so far. But if you turn on electrical field, there will be an anisotropy coming out, because there's dipole interaction no longer has spherical symmetry, right? You have this dipolar D1.D2 kind of and proportional to with the distance of R square or R cube. So this is the traditional P-wave barrier that I described earlier, of describing two molecules coming to collide when there is no electrical field. Now, if you add electrical field, the barrier is going to be heavily modified, because the molecules are not going to be oriented with respect to the electrical field. They're going to be look like this. But however, they can collide, for example, so-called head-on. You can see the two molecules being pulled into each other in attractive way by the electrical field. But they can also repel each other if the two dipoles coming side by side. So you can see this previously an isotropic landscape of P-wave barriers now become very anisotropic. You can have certain areas where the barrier is much higher, and in certain areas the barrier is much lower. Now, of course, in three-dimensional space, these molecules are moving around until they find the lowest spot for them to go in behind this barrier and have chemical reactions. And this is basically nothing. If you think about, I have a single partial wave to describe the collision, 1 h-bar unit of a P wave. But then in the 1 h-bar, you have 3 different projections. ML equals to plus minus 1. That actually describe this sort of a side-by-side collisional process. ML equals to 0. On the other hand, that component describes the head-to-tail collisional process, which is attractive. So you can see that we are studying collisions not only under individual partial waves, 1 h-bar, 3 h-bar, 5 h-bar unit of angular momentum, but we are also studying particular components of the 1 h bar unit of an angular momentum. And the different components have different manifestations of for the molecular loss. So if you study this, what you will see is that in 3 dimensions, as you increase the electric field, which increase the dipole moment in the lab frame, the loss rate increases tremendously by 2 orders of magnitude if you just improve the dipole moment by a factor of 2. And that's a big problem, right? It's indicating like there's huge loss. If I turn on dipole moment, the molecule just gets lost really fast. So all this discussion I had yesterday about, well, we can turn on dipole moment, you have elastic interactions, you can have anisotropic interaction, long range, you can study correlated quantum phenomena. All of that is not going to be realized if the molecules are gone. So you start to think about other techniques. For example, you can create molecules in 2D and have them being polarized with respect to the electric field that's perpendicular to the 2D plane. So these molecules, you force them to stand up, so such that their interactions mostly are repelling each other side by side. And you can see at least the loss is not dramatically increasing. It's maybe you can argue it's about staying the same. But towards the later part of my talk, I will give you a lot of exciting physics that we have explored this 2D confinement. And that taught us how to actually really turn on elastic interactions. And now we have gone back to 3D. Once you learned all these features of using electrical field to control the interactions, we can go back to 3D and still maintain a very low loss. So let me stop here for a second to see if there are any questions. If not, I can move on.
So there is one question from the very first part of your talk.
Yeah.
So the question is, could you please mention briefly how the 2 condensates are brought together adiabatically to enable the interactions between the species, and what the typical timelines of such cycle? Yeah, this process.
Yes. So how we brought, you must be referring to this particular slide. What we do is that these 2 condensates were brought together, well, I should rather call it, this is a condensate, this is the Fermi degenerate gas. We create them spatially overlapping on top of each other. And you can calculate the interparticle distance and how much what's the time scale they are colliding with. You try to make them thermalize between potassium and rubidium. And the time scale for converting is actually on the scale, a time scale of a millisecond or so. And the binding energy is typically on the scale of tens of kilohertz to 100 kilohertz. So millisecond is already sufficiently slow to make this process as adiabatically ramping through this collisional resonance of the Feshbach resonance to go from this initial free particles and up here, and they gradually adiabatically ramp into this red line, which is the first bound state below the threshold. And a typical time scale is about a millisecond. The time scale for the laser, this laser beams can be really fast. These are limited only by the power intensity you have, the so-called Rabi frequency. And this process can be on the order of tens or 100 microseconds. So that's all very fast on that time scale.
Okay. Thank you. Yeah. No other questions. Okay.
Good.
No, actually there is one more which has come up. So I'll just ask you. Does the loss change depending on how fast the electric field is turned on?
Yes. Yes. In fact, so far what I told you is a static process. What I told you here, it's all static. But indeed, if you want to talk about dynamical, as you turn on the electric field, if it's abrupt, there's also projection of a molecular state. Remember when you have electric field, you start to mix the parity states. So if you turn on abruptly, the initial state would have to be decomposed into 2 new eigenstates being addressed by the electric field. That's one part of the loss. The other part is actually if you do it adiabatically, then of course the remaining question is technical noise, which is is electrical field creating gradient and so on. So these are the processes I will describe a little bit later when we actually use electrical field to control the elastic collisions.
Okay, thank you.
Okay.
So I think you can go ahead. Yes, thank you.
So now I've been describing to you all this last problem, right? And now finally we get to going to address them. Well, one way to address this is to put them in three-dimensional optical lattices. Well, as indicated on the upper right, each molecule is living in one particular cell created by 3 pairs of laser beams, creating a three-dimensional optical lattice. So the idea is that you want to separate the molecules away from each other. And indeed, these molecules live much longer. I mean, they no longer, you're basically forbidding them from seeing each other such that they won't have chemical reactions. And even if the trap depth is not that strong, it's actually quite good, because if your molecules are cooled down to the so-called lowest Bloch band of the lattice, and I know that you're going to learn a lot from lattice physics in this summer school. There are some excellent lecturers going to tell you about lattice physics. I will tell you a little bit with molecules on the lattice, but here you can understand if these molecules are cooled to the lowest vibrational state of this optical lattice, and the fact that these are identical fermions would forbid these lattices from tunneling, these molecules from tunneling behind the lattice barrier to go from one to the other to have chemical reactions. And first of all, there's a Pauli exclusion principle. The second is actually that you probably have heard of this so-called quantum Zeno effect. The fact that the two molecules, if they come on top of each other, will have a chemical reactions, would in fact forbid them from coming to see each other, and they will stay put. And that's a really interesting counterintuitive, as if the molecules knows, if I go to my neighbor's house, both of us will be killed. No, of course the molecules doesn't know that, but it's actually that it's nothing mysterious here. It's really just a second order perturbation theory that if the molecules come on top of each other, there'll be a huge loss rate. That means that huge loss rate is much, much larger than the tunneling rate. And so in order for tunneling to take place, the huge loss rate actually puts a big barrier on the tunneling process because of the second order perturbation theory. Okay, so now you have these molecules living for a long time. We can actually think about doing so-called qubits. These molecules are, you have in the absolute ground rotational state, you can give a 2.2 gigahertz microwave photons. You can put them into a coherent superposition of down and up. Down up indicates ground rotational state and first excited rotational state. And of course, remember, between the ground and rotational excited state, it actually supports an electrical dipole moment D. There's a matrix element. It's the same matrix element that allow you to use microwave photon to couple these two rotational levels. And that means if you got these molecules in a three-dimensional optical lattices, you put them in this kind of a spin qubit, but also carries dipole moment, it actually gives rise to a very interesting lattice model of dipolar physics, where you can actually start to write down sort of Ising or spin Hamiltonians that has both this Ising interactions and spin exchange interactions. And the Ising interactions was with nothing but a spin that's separated by one lattice distance away. Spin exchange, meaning that if you have one molecules up, the other neighboring molecules down, they can exchange their spins. One goes up, the other one goes down, because they have this dipolar interactions mediating the two molecules. Even though they don't see each other physically, they don't have a short range physics, but they have this long range dipolar physics that can couple them. And of course, in front of it, there's a geometrical factor 1 minus 3 cosine squared theta, R1 minus R2 cube. This is what we learned from college level physics, is this so-called dipolar interaction geometrical factor. So this would be a full spin half Hamiltonian, a classic model that you can use to describe the quantum magnetism and so on, and the spin phase transitions. So it's, if you describe these in a three-dimensional lattice, in fact, there is no classical computer that can solve that problem. You would actually, that's one of the reasons for people working on quantum computers. This is a very much a quantum heavy sort of a parallel spin problem that you would need a lot of superpositions of your qubits to be able to solve such a phase transition, some stability dynamics of the spin physics. So I'm going to come back to this model from time to time to tell you that, but to just that you get this message that these molecules are no longer moving around in the lattice, but the physics, in fact, is very rich. Just because they have dipolar interactions, they can reach across neighboring cells for having a strongly interacting quantum system. So we did actually a very early study about eight years ago to study this dipolar spin lattice model. At the time, you can see that the filling is not very good. So we have these molecules. The filling is, as I drew here, is roughly correct. You know, you have only about less than 10% of the cell was filled with molecules. And nevertheless, it's actually enough already to study the first set of the dipolar physics in optical lattice. And what we do is we initially prepare the molecules in the absolute ground state, but then we turn on the microwave to put them into coherent superposition between the ground and excited state using a microwave home to drive it. And after you wait for a little while, these molecules get into entangled states because of the spin exchange, or in this case, we did not turn on DC electric field at the time, was limited capabilities to turn on DC electric field. So we didn't do that. We just turned on the microwave to make them into a coherent superposition of ground and excited rotational state. And because of the spin exchange interaction that I described earlier, these molecules, between the neighboring molecules, they start to have a spin exchange. And so if this molecule is in coherent superposition, like up and plus down, the neighbor also is up plus down, but then you can have a up turns into down and down turns into up. You can see the entanglement start to be generated. And then you can probe this by doing so-called Ramsey spectroscopy. You wait a certain time, E, capital T, that's the time. They waited a certain time, and you can probe the overall coherence of your system and see how it's decaying and how it's surviving, and so on. And turns out this is so-called Ramsey spectroscopy, and we actually put a spin echo in the middle just to remove any spatial anisotropy inhomogeneity in the system. So your Ramsey spectroscopy, you probably have heard about this. You initially it's a spin down. You apply pi over 2 poles, put it into a spin coherent superposition between up and down. You let it evolve for a certain time, T over 2. We do a spin flip. That's just the so-called spin echo that will remove the spatial inhomogeneity. If you don't want to deal with that, at the moment it's not important for you to understand the physics that I'm describing. And then you wait another T and a half. At that point, you can actually rotate your block vector and see whether the block vector is still strong or whether it's being decayed or whether there's lots of dephasing going on. So this spectroscopy sequence allow you to actually understand the decay of the contrast. For example, if you waited only 2 milliseconds, the contrast is nearly 100%. If you waited a 90 millisecond, the contrast start to come down. And if you actually plot the contrast as a function of the time, you see this kind of oscillatory behavior. And this oscillatory behavior becomes faster if you have more molecules, have higher density, higher filling. So what's going on? It turns out this oscillatory energy scale, it's oscillating every this 20 something millisecond, sorry. And that energy scale turns out to be, 50 hertz also turns out to be exactly that spin exchange interaction energy that I described in this model. The spin exchange, which is described by dipole-dipole interaction for molecules that's separated by one lattice cell. And this can all be calculated because we know the matrix element, we know the distance, and it's roughly 100 hertz. And so why we see a bit smaller, because it actually turns out to be half the scale of the interaction energy. 20 millisecond would correspond to 50 hertz. So let me just walk you through this entangling sequence of the two spins. You have each spin in a coherence position up and down. And you first apply, this is the way after you apply pi over 2. Now, if you look at the product of the wave functions, you have an up and down of the two molecules. And if you expand the wave function up in this cat language, you have then down, up, down, and down, up, right, after the first pi over 2 pulse. So this is it's a product state. You can still separate the two molecules as one molecule is up and down, the other molecule is also up and down. So this is still can be separated. It's a product state. It's not it's entangled state. But if you waited for a little while, and you will see that down, up, and down, up plus up, down have a slight different energy scale. Remember, up and down entertains the so-called spin exchange interaction. And so that spin exchange interaction will have, meaning that this energy scale will build up. If you waited a certain time, this energy scale will be building up compared to the down, and up. They do not have spin exchange interaction energy. So if you wait a certain time, like what I described here, T over A, 3T over A, the reason I'm describing T over A, 3T over A is just because we have a spin echo process, and you do not necessarily have to follow all of this complication, except you can see that there's a T over 2 together that we have weighted. So, but let me describe each individual pi over 2 pulses, which rotated around different block sphere axis. And usually the rotation is along Y, but now it's rotating along X. When I rotate along X, what I'm doing is I'm actually doing exchange. I'm exchanging up down plus down up into down plus up. Okay, so now you can imagine what I just did. I waited a certain time and for this to develop certain phase shift because the energy is different. At that point, I basically just exchange the two blocks. Up, down, up went into down, up. Down, up went into up, down plus down, up. So the phase factor just moved over from this side to this side, right? I just made an exchange. And then I wait for another time in between. And of course, when I wait there, this phase is fixed because the energy is a ground state. This energy, of course, develops again because there's a spin exchange interaction energy going on. So you develop a further phase shift. And then you can do another operation which allow you to exchange these two again. Remember, this is T over 16, this is T over 8. If you do another operation of rotation of pi over 2 along the x-axis, they exchange the phase factor again. So then you carry out this entire sequence, and what you will see is towards the end of these operations, I will be able to pull out the same phase shift factors, T over 8, T over 8, J is the exchange interaction energy, and then you can pull this back out. Once you pull this back out, it's no longer entangled. So the whole process I'm walking you through is to describe that if you had spin, we started it with two molecules, which is completely separated. And I described the process of, okay, you can expand it into the spaces. And this is still a separated basis, still product state between two molecules. But as soon as you let interaction, you wait a certain time with the exchange interaction, these molecules are now entangled. You can no longer write what's on the right-hand side into two separate molecules because there's a phase shift that's entangling these two molecules. And that's what you see in your Ramsey fringe. But by going through this sequence of pulses, I was able to disentangle the two molecules, basically by realigning all the phases. And I can, eventually I should be able to have this common phase factor in front of them. And this common phase factor can be pulled outside of the bracket such that the inner part is still down, up, plus up, down, and down, up. And that, can be made into a product state, just like up, down, multiplied up, down. And in that case, the molecular entanglement is broken. And you can see remarkably, this process I'm describing to you of entangling, disentangling, you can see in the spectroscopy signature, in the Ramsey fringe, for example, you no longer see this oscillatory behavior of the spin exchange between the two particles, and you just see a decay. Okay, I hope that you followed this. It's kind of a small trick to play, and this is the trick we actually borrowed from nuclear magnetic resonance field, where people do multiple pulse sequences to kind of disentangling the interactions. Furthermore, and you may still have a question, or why do you have the decay then? Why do you have this decay? Since you can disentangle the interaction, why does the blue thing is decaying? And now I'm going to describe why there's a decay of the phase. Turns out it's not a molecular decay. It's very different from the molecule number are not being going down, right? As we said, this is actually preserved. The lifetime is very long, but the phase, the contrast is still going down. Why? And turns out this is nothing but many-body physics now that I'm going to describe. And before I do that, it's just another interesting picture I can show you. You know, the excited rotational state has actually 3 sublevels: n-1, n equals to 1, -1, 0, +1. As 3 projections of n equals to 1 rotational state quantum number. 0 has only 1 projection, 0, 0. And so you can have the molecules rotating around each other like this, if their quantization axis is perpendicular, and you have 2 molecules rotating like that in the n equals to -1, -1. This dipolar interactions is actually slightly different than if I having the molecules prepared from 0, 0 to 1, 0. In that case, 0, 0 to 1, 0, the interaction is always sort of side by side, while 1, -1, the dipolar rotation is sort of a rotating. And if you average these 2 rotating side by side, sometimes the side by side attraction, sometimes it's a side by side, it's a repulsion. And on average, the 0, 0 to 1, -1 has a dipolar interaction energy of 51 hertz versus the one that's it's always perpendicular to each other. You have the 4 matrix element that's 100 hertz. And all of this turns out we can actually figure this out by looking at this decay. And remember, I was going to explain where the decay is coming from. It decay turns out actually coming from the fact that a molecule in the optical lattice, in a 3-dimensional optical lattice, it can have different neighbors. You know, you can have a neighbor that's to your right, which you can have an interaction of 106 hertz. And you can have a neighbor that's to your left, and again, so 100 hertz. But what if there's a neighbor sitting upstairs and sitting downstairs or living diagonally from you? So there's all these different frequencies, which could be 100 hertz, 50 hertz, or 100 hertz divided by square root of 2. All these numbers coming from the different geometrical factors. The fact that you're living in a large apartment complex, in a big building, and you have all your neighbors, and you know, whether they're left neighbor or your upstairs neighbor or downstairs neighbor, diagonal neighbor, they are making noises. You have all these kinds of noise hitting you, and that gives rise to this sort of decaying phase contrast of the Ramsey fringe. And so this is you can actually understand that the theory curve actually describes these various different contributions of interactions, dipole-dipole interaction. They're adding together to form a sort of a seemingly decay contrast of your Ramsey fringe. But in the end, it's a signature of the many-body physics mediated by dipolar long-range interactions. Okay, so this lattice physics, you know, at the time, 2013, 2014, we were able to have filling only about 5%, as I mentioned earlier. And you can think of, you got this egg cartoon, and it only like 6 eggs are in there. The dipolar interaction can connect neighboring particles, but if they have too much distance between them, then the interaction stops there. And so it's not enough filling. You would like to have a filling like maybe 20% or a little more, such that at this point, if you put it one molecule into a coherent superposition, that entanglement will be able to propagate out to cover the entire set of the molecules. Because as you can see on the right-hand side, not a single molecule, maybe the one that's out here, but most of the molecules always have a neighbor that they're going to have interactions, and you cannot really escape anymore. This is what people call the population threshold, where that you can no longer have a particular corner of your material that's not part of the interactions of the entire set of the material. So one of the goals to go to higher lattice filling, and one thing that we actually attempted at the time 5 or so years ago is to making molecules directly inside the optical lattices, and it's essentially the idea being let me prepare so-called insulator, band insulator, and a mod insulator, where I have rubidium atoms indicated by the red balls are filled on every single lattice site, and I can do that because I can make rubidium BEC exceedingly low entropy, so the filling can be really, really good. And the potassium molecules we can make also fairly low entropy, make the so-called Fermionic band insulator. And what you're seeing is on the optical lattice, 3-dimensional optical lattice, at each lattice site, we can have one atom each, one rubidium atom, one potassium atom. And then you can go through this association process, magnetic optical association, and you can create KIB molecules with a 25% filling. And that was the work we did in 2015. At the time, that technique sort of run to the end of the what we could do. Maybe we can improve by another factor of 2 at most, 50% filling, but felt that was, we only were able to make 1,000 molecules at the time. So it felt like that was a particular stage where we probably should find different ways of doing it. And that this actually starts the next generation experiment. Before I go on to talk to you about the next generation experiment, which started around 2016, and it has given us now a lot of new results. But before I get into that, let me just stop here and ask whether there are questions.